So today's class is mostly recall, but these are important. Lecture 20. So recall. So how we define projective varieties? So first we define what is called projective space. So whenever you say projective space, it's a topological space. So first, what is the underlying set? Underlying set. So notation is Pn. The set theoretically, this is nothing but say Pnk or Pnc. So this is you take the affine space, take the 0 point out, and then you have this equivalence relation that any 2 points on the line joining passing through origin, they are same, right? So as I said, this is as a set, but as you know that just set is not a good enough object. You need to define a topology. So all algebraic varieties, they have a topology. So how did you give a topological space? So for that you need to introduce what is called graded ring. So you consider the graded ring K x naught xn. So this you can write it as direct sum of the homogeneous polynomial, where SD is degree D homogeneous polynomials. Okay, and with SD you attach 0, so then it becomes a vector space. So it's a direct sum of. So this is a graded. So if you have two homogeneous polynomials, you can multiply. So if you take the multiplication, then SD then goes to SD plus E. So this is a graded multiplication. That's how you define. So this is a graded ring. So now, so you take an ideal, say in S, you say it is a homogeneous ideal. It's called a homogeneous ideal. If the generators, or if it is generated by homogeneous polynomials, if I is generated by homogeneous elements. So sometime I write S of H as a subset, the set of all homogeneous elements. Okay. This is not a subring, because if you take two homogeneous elements, then their sum may not be homogeneous and all. So it's just a set. This has no structure, algebraic structure. But you say that it's a homogeneous ideal. It's not that all elements of I are homogeneous. It is the generators. It is generated by homogeneous ideal. Which are homogeneous elements. So in particular, so if you have a T, say suppose T is a subset of homogeneous elements. So let's write T is a subset of. So S of H is set of all the homogeneous elements of S. So if you take a sub T of a subset of homogeneous elements, then you can define what is called the algebraic set. So you define V of T. So now the point is that if it is a homogeneous element, then it makes sense. Zero set of a homogeneous polynomial, right? So then you consider P of P in Pn. such that f of p equal to 0 for all f belongs to T. This is a well-defined object because you are taking the 0 set. Okay. So now these are called, so this is a subset of Pn. So this is called algebraic set, right? These are called algebraic sets. So if you start with some subset of homogeneous element, in particular if I take any homogeneous ideal, so then take the generators of the homogeneous ideal. It is generated by some homogeneous elements. So take corresponding V of T. So that will be a algebraic subset of Pn. Huh? S of H is set of all homogeneous elements of S. Yeah, S is the polynomial, right? S is the polynomial ring. So they are homogeneous polynomials.
How is the zero set of ideal? The zero set of ideal, how will you define?
Yeah, so you take, that's what I am going to define now. So what is so if you take a ideal I is homogeneous ideal in S. Then V of I you define to be the V of the generators of I, the homogeneous generators of I. And it is well defined. You have to check that if you take two generators which generate the same ideal, then they are same. Okay, so that's how you define. So V of, so if it is a homogeneous ideal, so is a V of let me write like this, that homogeneous generators of I, and this is well defined, check. That means if you take two generators which generate the same ideal, then V will be same. Because one will be written as sum of other elements and similarly, so that's how you define, right? If F is, something is a subset of this, then the V of, so this is the easy exercise, you see that this is a well defined. Okay. So now it has those, so now, so this is a subset here in Pn. So you define these are algebraic sets, these are your closed subsets, right? And then this forms a topology. So now to show that, so what you have to know, that if you take two such homogeneous ideal Vi1 and Vi2, then their intersection is nothing but V of I1, I2. That we know. If you take two ideal I1, I2. But if I1 is homogeneous, I2 is homogeneous, then I1, I2 is also homogeneous. Because I1 is generated by homogeneous polynomials, I2 is generated, so I1, I2 will be generated by the product, right? Product of the generator. So they are also homogeneous. And this is about unit, and if you take intersection, say V of I alpha, then this will be V of a union of T alpha, but T alpha is T alpha the homogeneous generators of I alpha, right? I alpha is generated by some set of homogeneous elements, so it will be V of union. So, so this is also set of all homogeneous, T alphas are homogeneous subsets, so union, this is also homogeneous. Huh? What? Yeah, but that will be same as V of union TL. The way I define it using the homogeneous element, that's why I am writing like this. Okay, and the V of the empty set and V of the unit ideal, they corresponds to the V of 0 and V of the unit ideal, they corresponds to the whole Pn and the empty set. So V of so 0 is a homogeneous element. So V of 0 is the entire Pn, and V of 1 is your constants are also considered homogeneous. Sorry, empty. So this forms a topology. So this we have seen. I mean those things.
Why we took the grading? We could have just taken the ring and take the homogeneous polynomial.
You will see why it is important. The grading is important. You will see. One of the reason is that to have Hilbert-Nullstellensatz. See, it is a correspond. So you know the Hilbert-Nullstellensatz in the affine case is just prime ideals. So here not just prime ideal, it is called homogeneous prime ideal, and the grading of the idea that it's a prime graded ideal. So the quotient also has a grading, and this grading is important because I will come to this. This is an important question. Why grading is important? When we do some example, for example, within a moment we will see why grading is important. But this is a very nice. This is a very good question. So, okay. So now this is the from the ideal side you come to the zero set. Now the converse. So now if you take a subset, so if you take a subset y in Pn, you take any subset, then you can talk about I of y. What is I of y? I of y is the ideal generated by set of all homogeneous element which vanishes on y. So this is f of f belongs to S, H, such that f of y equal to 0. Now, this may not be an ideal, but you take the ideal generated by this. So, you take all the homogeneous polynomial which vanishes on this y and take the ideal generated by that. So, this will be a ideal here. Now, the point is that if you have an ideal of a graded ring that give Iy, so if you take SD, S is, you can write it as sum of degree D polynomials, homogeneous polynomial. Then Iy gets also a natural grading, right? Where Iyd is nothing but Iy intersection SD. This is standard. It is just for any module. It is true. If you take M is a graded module, then take sub module, then that also gets a natural grading. Now you can talk about, because of this Iy is also a graded ideal. So now you can talk about S modulo Iy. This is also a graded ring, because Iy is a graded idea, graded sub-ideal of S. So that makes, so you call this Ay or Sy. So this is called homogeneous coordinate ring. Homogeneous coordinate ring of Y. Okay. And this is also a graded ring, because Sy, then Syd you can write it as Syd you can write it as direct sum of St modulo Iy of D. This is also a graded ring. So okay. So on P and K you have a topology. Now you say that Y is a projective variety. If it is a closed subset, Y is called projective variety. So this is for any subset. Now you call that Y in P and K is a projective variety. If it's a algebraic if it is a if it is irreducible, if it is an irreducible algebraic subset. Irreducible as a topological space, and the Y gets a natural topology induced by the Zariski topology on the projective space. Okay. So now once you have some topological space, now you want to know what are the functions on projective variety. So regular functions basically. So functions from Y to K, right. So now so if you take any homogeneous polynomial f for any f belongs to, so you can define what is called D plus f. So D plus f is all the point P in Pn such that f of P is not 0. Right. So this is nothing but your Pn minus the 0 set of f, the ideal generated by f. So f is a homogeneous polynomial, take the ideal generated, so that's also a homogeneous ideal. So now you remember that you take, so you call it the what did I call standard open subset or standard, what was my definition? Not basic open set. These are called basic open sets. This forms a basis. Of Pn. That means any open set you can write it as union of D, but there are some standard. So if you take f to be xi, so then ui you define to be D plus of xi. So you take the coordinate function x. So Pn you have x0, x1, xn. You consider D plus of xi. Xi is a homogeneous polynomial, so it's a linear polynomial of degree 1. You consider D plus of xi. So this is set of all points where the xith coordinate is non-zero. So this you can identify with the points like x0. Just write a0, a1, 1, ai plus 1. This is ai minus 1. An. Right. Now this ui, so this is a upright, so this is a open subset in Pn, and this is a quasi-projective variety. So what is a quasi-projective? Quasi-projective is the open subset of any projective variety is called quasi-projective, like quasi-affine. So Pn is a projective variety because it is 0 set of some zero polynomial. So it's a projective, and that's a So that's it's irreducible also. Pn is irreducible. You cannot write as union of two closed subsets. That is, so when I write irreducible, yeah, or so yeah, that is also another way of saying that projective varieties and of projective varieties in Pn and prime ideal, homogeneous prime ideal, that is there is a one-to-one correspondence. So I'll give as exercise those things in my zeros of the prime ideal. Yes. So if it is a irreducible subset in Pn, that means the I of y should be a homogeneous prime ideal. What is homogeneous prime ideal? Which is prime ideal and it is homogeneous. So I'll give few exercises, then those things I'll not do in detail, because mostly it is affine analog. Okay, but I'll leave it as exercise. I'll give. Huh? Yeah, I did. So that's why I said that mostly I will do recall, but because I want to start morphisms, morphisms of projective value I have not done. So, but to do that, I recall all these things, because these are required to. So this UI, you know that this there is a map I define from AN, map called psi I, right? So in this direction, I think I defined. The map was that I take okay, this is psi I from ANK to UI. So map is that you take any element A1, AN. So what you do, you send it to okay. So okay, you do this A1 colon A2 colon AN, and here you put 1. Sorry, not AN, AI minus 1. And here you put I plus 1 AN. But obviously this point is in UI. And similarly, if you take a point here, say B0, B1, 1, Bn, then you send it to B0, Bn. So here Bi minus 1, here Bi up to Bn. So ith position 1 is, we just omit. And this is a bijection. We show that this is a bijection. And we have seen that this is, so now UI is a open subset in Pnk. So this is a quasi-projective variety. And this is a affine variety. So as a topological, both are as a topological space in its own right. Right. What we have seen that this is a homeomorphism. Right. So we saw that you have seen psi I is homeomorphism. Right. But homeomorphism does not mean isomorphism. Be careful. We have not proved that this psi I is a actual. So this is a project. So you have a, so to define isomorphism, I have to go to the what is called morphism. So, but the point is that you remember that affine variety, affine is inside quasi-affine because of this homeomorphism, and this is in quasi-affine, they are in quasi-projective. And of course, projectives are here. So, So this is as a affine variety, so they are quasi-projective, right? So this morphism we have not seen that it is a isomer. So you can ask whether it is a morphism or not. So the point is that this map is not only morphism, it's also an isomorphism. Isomorphism in the category of quasi-projective varieties, right? Because UI is a quasi-projective variety. So if you take a affine variety, this is affine variety. So this is also a quasi-projective variety, and this map is a map of quasi-projective varieties. And the point is that this is an isomorphism of quasi-projective varieties. Or in other words, once it is isomorphic, then UI also becomes a affine variety. Which way you look at it. So this is a, and so we will see that this is isomorphism. We saw that it is an homeomorphism. Yeah. So this is the point. So psi I is isomorphism. So to say the isomorphism, first what we need to know what is the regular functions, right? That's how you define that morphism between two varieties. It takes regular functions to regular functions. So isomorphism is a morphism which has an inverse such that compositions are identity. So first, what is a regular function? To say that it is isomorphism of quasi-projective variety. So what is the morphism between in the category of quasi-projective variety? So that is the next. And another thing I also did this, that there is some bijection between closed subsets here and the closed subsets here. So this is a result. So this I'll write it as a lemma. We will come to the proof little bit after some time.